Welcome everyone. Thank you for taking the time to join us for this webinar session. My name is Denis, and I will moderate today's webinar with the subject, the future of high-speed substrate, the cutting edge of adhesion promotion. First and foremost, I would like to introduce to you Thomas, who is our speaker and subject expert. Thomas joined the company back in 2014 as R&D scientist, until he was appointed in his current role as a global product manager for our surface treatment technology division. He is a true expert in his field, and we are excited to have him here with us today. A couple of words about the webinar. The webinar will be divided into two parts, 35 minutes presentation and 15 minutes Q&A session. I encourage you to raise questions from the beginning of the presentation and therefore to use the Q&A function, which you can find on the top right corner of your screen. Your questions will be visible to me and Thomas, therefore do not hesitate to ask any related to the topic questions. We'll try to cover as many questions as possible during the planned Q&A session at the end of the presentation. If the time allows, we will answer all questions right away. Also, Thomas will be available after the webinar to reach out to you via email. Last but not least, if you face any technical issues, please make sure to enter the webinar via the latest versions of Chrome or Firefox browsers. Now let me hand over to Thomas. Please enjoy the session.
Thank you, Denis, for the kind introductions. Good afternoon for all of you in Asia. Good morning and good noon for all of you in Europe and India. So welcome to the webinar presentations about the future of high-speed substrates. So as we all familiar with, that the adhesion of copper and dielectric is very important in IC substrate manufacturing, especially when we are talking about interlayer bonding. Many methods has been published or has been presented, and yeah, with this cover like a mechanical bonding and also chemical bonding. And right now, for today, I would like to introduce you the latest development, what Atotech has been developed in order to have these adhesion promotions to increase the adhesions for the inner layer bonding. I would like to start my presentation by giving you some introductions and background why we are doing so, and what is what based on what that we are targeting ourselves for different kind of roughness and also different kind of materials that we would like to achieve, and for what kind of application is that. And next, I would like to follow with what Atotech STT can give you as a solutions. I will start with one of the product called Novabond EX, which is targeted low etching for high-speed substrate applications. And then we try to push ourselves into the border to even go lower with the etching and also the roughness, which will be the second solution of this topic today, is Novabond EX plus WJ. And at the end of the presentation, I would like to wrap up my presentations by giving you a summary. Follow the development of electronics industry, which is everybody knows about miniaturization. So everything is getting smaller and smaller. Mobile phone, computer are getting smaller, but they need to become smarter. So that's what it means for the IC substrate, is what we're using as a processor afterwards. That the dimensions of the line and space is getting finer and finer, where nowadays they can already achieve, sometimes you can hear already about 9 to 12 micrometer by SAP technologies. In the future, they're targeting 3 micrometer, or even in 2022, probably 2 micrometer. And that means that, in the term of etching properties or etching amount in the process, we need to go even lower and lower, which is nowadays mostly you're using 1 micrometer or 0.5 micrometer, but it's a minimum. But in the future, we need even to go lower, down to eventually non-etching or zero removal of the copper. As the solutions, many often of the adhesion enhancements, they are based on the oxide replacements, or also as the adhesion promoter that you put something on the top of the copper. any kind of species that you put on the copper, they have a potential to create an undercut, or we call it twist wedge. Or very often also, if you take a look from the top in the 2 dimensions directions, you can see like a ping ring we call. So this we call is the undercut or wedge, which is the requirement for nowadays is at least 10% of the blind microfire diameter. And eventually, of course, in the future will be no wedge for it allowed. Yeah. Because of the applications for the such kind of substrate for the high speed. So I mean that we move from the low frequency to the high frequency. So what is very important effect or factor in this is the roughness of the conductor. So that's the reason why the roughness of the conductor as well need to be even lower and lower, which is right now allowed roughness is around 200, 300 nanometer, but in the future it will be down to 50, only 100 nanometer, I mean that lower than 100 nanometer. That means that's no roughness changing anymore. We just keep this an original, and what kind of process that we develop in the future will be no roughening, sort of speak. So Atotech can provide Nova 1 series product to cover those spectrum of the requirement from 2019 or from this year, from the current until for the future, which is targeting for the low roughness, low etching. But still, we need to remember that we need to keep the good performance from our POR. It means that good field strength, good thermal reliability, and also good process stability or capability. Not only talking about the fine line because of miniaturizations, we also, as I mentioned before, is the high frequency. So because the technology shift, I mean that the transition, we are in the transition from 4G to 5G. So in the 5G, as we know that all about connections, right? So all the smartphones, smart TV, smart home, any kind of smart devices, they try to communicate to each other, and that's the reason why we need. They will create a very enormous big volume data traffic, and not only the volume of the traffic data that will be created, but also we need to take care of the speed of the data transfer. So if we have a lot of data, but we have a slow data transfer, that is kind of useless. So that's why in the future also we need the high-speed data transfer. So in this case, we need to see from the low frequency, which is we are using right now, actually available right now, and to move to a high frequency, which is as listed in here is around 30 gigahertz or even higher. And this kind of high frequency application bring us to the new challenge in terms of adhesion enhancements or adhesion promotion process. So why I said that? Because the most common adhesion promotion method is based on the surface roughness, where you can create a mechanical anchoring afterwards to enhance the adhesions. So right now, if we take a look on the plots of this skin depth, from the skin depth, we can see, because the skin depth can explain about so-called a skin effect. So what is that? And then from the skin depth, we can see at the low frequencies, this depth, I mean that how the electron of the signal, let's call it the signal from right now, how the signal move inside of the conductor. So at low frequency, they still inside of the bulk. I mean that deeper, I mean that just move inside of the bulk. So it means that if the surface is rough, they don't see the surface morphology. They don't see this profile. They just move straight like a line here, like the line here. So it means that the length of the signal is, as what you see from the bulk. So as we go to the higher frequency, the higher the frequency, you can see that the skin depth is getting thinner and thinner. So it means that the signal prefer to move around the surface, along the surface. So that's the reason why if we have a surface morphology which is rough, you will increase the length or the path or the signal path of the signal will travel to. So there will be a delay, or either there's a potential of the signal loss. Just want to show you experimentally what we did with the rough surface compared to the smooth surface. As you can see in here, when we try to measure this insertion loss or the signal loss, so-called, and at low frequency, we don't have so much difference between the rough and the smooth surface. But as soon as you go to the higher frequency, the higher the frequency, the insertion loss will be split. For the smooth surface, you will have much less insertion loss or signal loss compared to the rough surface. That's the reason why for the high frequency application, it is really recommended, or it is necessary actually, to move from the rough to the smooth surface. Yeah, as an Autotech surface treatment technology, we are developing a different method how to enhance the adhesion for interlayer bonding. And one of the solutions, what we bringing up in here is to launch the product called NovaBond series, NovaBond HF for high frequency, EX with adhesion promoter, and the other NovaBond EX, even we push our boundary to go even lower with the roughness. The target of this development is, of course, to follow the requirement of the electronic industry outside there for IC substrate high speed. So you could see that the edge step is getting lower and lower. So we targeted like 0.2 and 0.4, and eventually we would like to have very minimized. So it's like 50 or 150 micrometer for NovaBond EX plus WJ. Of course, this is also reflect not only because of the not only edge step, because of the high frequency application for the high speed substrate. So it means that the roughness has to be also minimized, which is our target will be as what you see from the roadmap before, that will be lower than 100 nanometer or lower than 0.1 micrometer. And to give you some background in here, that what kind of system is that in NovaBond HF and NovaBond EX is based on the ferric iron, so it's an iron sulfate-based etching solutions, where we put the organic because you know that when we lower the roughness, because most of the adhesion is based on the mechanical anchoring, the lower the roughness, the lower the adhesions. That's true. If you don't put the chemical adhesion or adhesion promoter, then that will be the case. So that's the reason why for NovaBond HF, NovaBond EX, we put adhesion promoter on the top in order to bring back again the concept of the adhesions into the system to enhance the adhesion even more. Okay, so for NovaBond EX plus WJ is slightly different. It's based on hydrogen peroxide sulfuric acids, but still more or less going to the same directions on a much lower roughness. But at the end, we put the adhesion promoter to enhance the adhesion further. Now, I would like to start to give you more deep introductions about NovaBond EX. So NovaBond EX, ferric iron-based chemistry, target for the ultra-low roughness because the application is for high-speed substrate. Yeah. In NovaBond EX, we try to bring the best out of adhesion concept. I mean that mechanical adhesions, which is created by the mechanical anchoring from the surface roughness, but we need to minimize them in order to fulfill the future requirement of applications. And at the same time, we bring the adhesion promoter, which can give us the chemical concept, I mean that chemical adhesion later on, to bring back again these adhesions to the level where we can pass the requirement and also a good thermal reliability at the end in the layer bonding. So this adhesion promoter in NovaBond EX is a kind of organosilane coating. So this organosilane coating is used to be a chemical bonding bridge between the copper and the afterwards laminate polymeric materials. Start with the cleaning the surface, so because we need to make sure before the input samples, before the samples goes to our NovaBond EX process, we need to make sure that all clean surface that we are dealing with. So in here we have one cleaner, which is only acidic cleaner. The purpose of this acidic cleaner is only removal of the copper oxide, to make sure that all of oxides will remove and to make sure that it will be clean enough to go to our novel bond AX process. And you could see in here that the conditioner step is as the second step. This is the only place where we remove some part of the copper, which is in around 100 until 200 nanometer, to create a very smooth roughness, which is later on can be used as a chemical, as a mechanical, as a mechanical adhesion or mechanical contributions to the adhesion because of the mechanical anchoring. Pre-coating that we need to use as the name, from the name you can see that the pre-coating is to prepare the surface in order to have a proper adsorption later on to the coating, which is the coating is the real adhesion promoter, which we use as a glue. If you try to think about as a glue, which is only in nanoscale glue. By the coating, I mean that the coating part is the one which is contribute to chemical bonding or giving the chemical adhesion later on. The surface roughness of the novel bond EX, because we are using lower edge step and also the target is lower roughness. And you can see in here, we try to compare to the POR outside for inner layer bonding for IC substrate. So cupric chloride base of action. Our novel bond EX definitely, you can see from RA, RZ, RQ, all, is much, much lower. Yeah, that's the reason why this process novel bond EX, because of the lower surface morphology or surface roughness properties, can be a good solution for the high speed substrate applications. And as of one of the factor, of course, which is I didn't show in here, that the factor of the high speed, I mean that for the high frequency, for the signal loss, is not only the roughness, but also the line width reduction. This is very important, which is take part some percentage in, I mean that in affecting the signal loss in the high frequency applications. So that's why we investigate in here novel bond EX. When we try to compare to cupric chloride actions, our line width reduction is almost 10 times less, because the fact that we are using only 10 times less of edge depth into the process. So that's why then by reducing the edge line width reduction, we could reduce also the signal loss performance. Or in other way around, we increase the signal integrity performance. Going back again, as I mentioned, we lower the roughness for the high speed of substrate applications, but still we need to maintain the original performance, right? So the build strength have to be the same as before, as the other POR. So as you can see in here, when we have been trying, novel bond EX has been tested on different kind of materials for IC substrate future right now, nowadays, and also for the future applications of IC substrate materials. So I think some of them you're really familiar with, and some of them not, because they are still development stage for the future application of lamination material for IC substrate. And you could see that all of them, maybe I need to give introductions about the fuel cure only. The fuel cure only, maybe I just point out in here, is only after the initial adhesions, and Haas means the pill strength after reliability tests, the Haas test with the humidity. So if you can see in here that all of those materials that have been tested for with novel bond EX, we have a good pill strength, really high pill strength, much higher than what our material supplier, which is in here, is from it is Ajinomoto with the IBF, is much higher than what they required. So and also after Haas test, you could see that our drop of adhesions, I can say there is no significant drop of adhesion after the Haas test. So you could see how good is the novel bond EX performance in terms of pill strength and also thermal reliability or humidity reliability. Another factor which is very important, as I mentioned before, because usually the weakest part of these after the adhesions is what is on the interface. So what we call very often in acid substrate manufacturing is the wedge voids, or you also can call it halo, some of them, if you take a look from the top. So from the wedge voids performance in here, we try to black and white comparisons. So first I need to emphasize that the material that we are using is IBF GX231, which is actual has been used, it has been using for the production for as a substrate. It's very commonly used right now. The thickness is only 10 micrometer. The reason in here why we pick the 10 micrometer is because, we just go to the harshest conditions ever. So when the material is thinner, so it means that it's more air or more humidity can be penetrate inside of the materials and attacking at the interface. And black and white comparison in here, if you take a look on the left-hand side, without Novabond EX, and if we try to compare to what is with Novabond EX, you can see that without with Novabond EX, we could significantly improve the wedge voids performance. It means that we can significantly reduce the attack or any kind of chemical attack or oxidation, what has happened at the interface. So without Novabond EX is around almost 12 micrometer or 30 micrometer. And then with Novabond EX is only around 2 until 2.5 micrometer. Last, what is very important, of course, we are always talking about high-speed substrates. So we need to show about how about the performance on the signal integrity, isn't it? So in signal integrity in here, we try to represent in the way that we show the signal loss. So the higher the number in negative, it means that more signal loss. And the lower the number in the negative means that the lower of the signal loss, the lowest the signal loss. That's what we want to target it then, the lower the number. And it was measured at 20 gigahertz. It was targeted by one of our customer. And the material that has been laminated on the top is Doosan 7409 DVN. This is very commonly used for high frequency application materials. You could see in here that our signal loss performance is more advanced than one of our high frequency product. It is for oxide replacement for high frequency product. We have a significantly improved by Novabond EX due to the much lower surface roughness. And when we try to compare to the non-etching one as a reference, we are almost at the same level. So I can say we are at the same level. The Novabond EX is not only good because of the surface roughness, high signal, good for the high for signal integrity performance, but also can maintain a good performance in terms of peel strength and also improve wedge voids at the interface surrounding the blind microfire. The next product that I would like to introduce to you is the Novabond EX plus WJ. So if you're trying to guess, yes, and the combination of Novabond EX, what I've already introduced to you, plus WJ is the new pretreatment. The concept in here, or the purpose in here is to, in order to offer the lowest possible surface roughness that we can provide it for the high-speed substrate or high-frequency applications. So it's based on sulfuric acid hydrogen peroxide chemistry. The target is very ultra low roughness for the high-speed substrate. But still, we need to maintain the good peel strength and also the other performances. Again, the concept is to bring the best two different concepts, mechanical anchoring and also the adhesion, the chemical adhesion by the chemical bonding by introducing the adhesion molecule. So whereby very unique surface that we create by the Novabond EX plus WJ. So the nanostructure that WJ provide is very unique. So we will have increased low roughness, low edge depth, but we still can have a very low surface area increase, the surface area, which just means that you will have more anchoring spots between the copper and the polymeric lamination materials. And the next step, after we create the nanostructure on the surface of the copper, there will be the adhesion molecules, which is giving you contribution to the chemical adhesions as a bridge, again, as a bridge of the chemical bonding between copper and ABF. Similar to Novaboni EX, it consists of 4 process steps, which we start with the cleaner. Every process that we have been developed is always start with the cleaner to remove the oxide to make sure the surface is ready for our next step of the process. So it means that conditioner WJ. And conditioner WJ is very unique process where we can create a very little removal of the copper, which is only 50 until 100 nanometer, but you can create a very high surface area after the process. So the pre-coating again is as the name you can see to prepare the surface in order to have a really good to increase the absorption of the coating as the coating as an adhesion promoter in here. So the adhesion promoter, the coating is the real adhesion promoter, which is later on can enhance chemically by providing chemical bonding between copper and ABF materials. Also, the unique features of this process is because of the analysis. So the analysis is very simple. As you can see in here in the conditioner step, you only can, just measure the wet loss because that's the way that you remove the copper, and then you try to measure how much copper that you remove. So that's the way that we define the edge step, or how much copper that we remove. That's the way that we control the conditioner. And the second, which is a little bit sophisticated but still easy, is the organosilane adhesion promoter, where we call it with the coating. Adhesion coating, organic coating as adhesion promoter, and we can measure via FTIR. Of course, we have developed also different methods that we can try to measure or try to as a quality control of the adhesion promoter coating, but still the most reliable and also the most convenient one for us, also mostly available as not mostly, but some of our customers is the FTIR, where we can see in here, try to demonstrate to you how we try to measure in here. There's a specific bandwidth of, which is our molecule can give a signal. And if you take a look in here, by increasing the concentrations, that we also can increase those, signal. So that's the way that we try to define, how thick is the layer of the adhesion promoter of organosilane on the top of our copper surface, and how good is the quality of the coverage of those coating on the surface. The roughness of WJ, if you can see in here, just look it up on the left to the right from what is initially when we just received the sample, and also after the WJ process, or Novaboni EX WJ process. You can see in here is actually their surface roughness in terms of, first I would like to emphasize that we measure by AFM. The surface roughness by in terms of SA is not so much difference. It's only some nanometer increase. But if you take a look on the SAI, you can see how significantly improve or how significantly increase the SAI from 15% goes to 40% for Novaboni EX plus WJ. So the secret in here is to keep the roughness as much as possible, but we need to increase the surface area in order to give a better mechanical anchoring afterwards with lamination materials, nano roughening. Again, now we come up with the pill strength results. So how good is the pill strength for such a process, even though we really significantly reduce the roughness compared to the POR? So I would like to show in here is the influence of, this process, Novaboni EX plus WJs have to be one. So pretreatment also will influence the performance of adhesions. And and also the coating adhesion promoter also will influence the performance of the adhesion. So in here, I would like to show you the first part first. So how the surface pretreatment by WJ, which is this nano roughening, the unique surface creations, can influence the pill strength. So we demonstrate on two different materials. One material is TXT31, which is actually used, currently used for the production of acid substrate. And the other IBX, I'm sorry, I cannot mention in here, is GYXX only. This is still under development, so will be used for the future acid substrate productions. So for both cases, you could see that how significant Novabond WJ process, I mean that the WJ pretreatment can influence the pill strength. So initially, maybe we can say not so much different. So only 2 or 3, only 1 or 2 Newton per centimeter different. But when we have a look on the Haas or after humidity test, you could see a significant drop if we don't apply the pretreatment WJ. So 50%, so half of it already gone. So, but when we apply the pretreatment WJ, you could see the drop is not significantly. It's only around 1 Newton per centimeter. Usually we define as an error in our measurement. And also for the other materials, for GYXX, the same behavior you could see that with pretreatment WJ, without pretreatment WJ, the pill strength will significantly drop after the Haas, while with WJ, pretreatment WJ, there is no significant drop of adhesion after the Haas. Good adhesion, excellent. And now we coming to the adhesion promoter. Do we really need the adhesion promoter? Maybe WJ only is enough, right? Pretreatment is no. So in the answer in here is no. The coating, the adhesion promoter, which is contribute to chemical adhesions. This is the one that we needed as well in combination with pretreatment WJ. As you can see in here also the way that we try to demonstrate the same. So one material from the currently used and for the future applications. And when you look it up without the coating, so in here you could see the drop of the adhesions. Again, almost about 50%. So initially it's almost the same between the WJ with silane coating or without silane coating is almost the same level. But after the Haas, you could see a significant drop when we don't put the adhesion coating on the top. But when we put the adhesion coating on the top, we only can see only slightly drop of adhesion, which is almost in the error bar there. Also the same behavior we could observe for the other materials. Yeah. Also, no significant drop of adhesions after the Haas when we apply the silane coating on the top. So I could conclude that Novabond EX plus WJ can provide excellent adhesion for different kind of materials used for acid substrate production. Requested by one of our OEM because the only pill strength, roughness, this kind of criteria is not enough. So we need to take a look on the real sample. So when we have like the real pattern sample, how it looks like. So one of the requirement is they would like to see if we do have the sidewall delamination or not. So sidewall delamination happens beside of the tracks with the lamination materials. That's also what they observe when they apply such a system, which is low roughness adhesion promoter. So indeed in here you could see from the pictures that we didn't observe any delamination. There is no gap between copper and IBF material. So no or free sidewall delaminations. And the next one will be the line width reductions. So what we can see in here from the line on space 5 to 5 micrometer. So there is no significant, initially is on the left-hand side. And after WJ is on the right-hand side. So you could see no significant, or I can say that zero line width reductions after the Novabond EX plus WJ process. And the last one, which is they really interested about, is about the halo or the wedge voids. next to the blind microfire. You could see that with the Nova 1EX plus WJ, almost no halo or no wedge voids or much reduced. So Nova 1EX plus WJ can significantly improve the performance of the wedge voids. Means that to reduce significantly the length of the wedge void. Like to demonstrate because 5 to 5 micrometer, yeah, obviously is not enough because from the future roadmap, you can take a look that, yeah, 2021, we can still use 5.5, but in the future, they would like to go even 3.3 or 2.2 micrometer line and space. So in here, we also try to demonstrate with how about the line and space 2.2 micrometer. You could see when we try to compare with our conventional etching, it is around 0.2. After the treatment, if you compare to the non-treated one, it's a lot of removal of the copper, and then almost some of them, they already leave it off from the board. But with WJ Nova 1EX plus WJ process, so it doesn't matter which step, we try to go with different two kinds of edge step to see the influence of the edge step on the line width reductions. You could see there is no significant for all of them. Doesn't matter how, and yeah, there's no line width reductions. So WJ Nova 1EX WJ is only creating a very unique rough nanostructuring surface on the copper surface. Very suitable for the future very fine line applications. And again, last but not least, for the high frequency application, high speed substrate, we are always concerned about the insertion loss. In here again, we measure, our customer measure, which is Mectron 6 was laminated on the top, and the measured frequency is slightly higher than our 1EX, which is 25 gigahertz in here. And you could see that compared to our oxide replacement, raw roughness, which is a solution for the high frequency for oxide replacement, we could significantly improve, much more improve with the Nova 1EX plus WJ. And you can see in here that we are at the same level as a reference, which is non-etching. So before any kind of process, which is non-roughening at all. I mean that our signal integrity performance or insertion loss performance is more or less on the same level as non-etching for Nova 1EX plus WJ. Right, with this, I already introduced you about two of our solutions for adhesion promotion for the low roughening IC substrate for high-speed applications. And I would like to summarize. One is ultra low etching adhesion promoter, what I have been showing you before. The target is, of course, the roughness is, as I show as well, the roughness is lower than 100 nanometer. And very minimum, or even with Nova 1 WJ and Nova 1EX WJs, there is no line width reductions can be observed. That's the reason why with this kind of properties and also this kind of low roughening surface morphology is very suitable for high-speed substrate applications, which can significantly improve the signal integrity performance, of course. And of course, that as I shown before, low roughness, we improve all of the surface morphology, but we still maintain a good functional performance in here, which is adhesion performance, and also superior thermal reliability. And the material compatibility, as I showed before, that we are really in the good compatibility, very good compatibility with different kind of ABS material. It's targeted with the low decay and low DF material, which is targeted for high frequency or high speed substrate application, of course. That's all my presentation for today after introducing Nova 1EX and WJ. And I would like to enter now with the Q&A sessions. If you have any questions, please feel free to ask, and I will do my best to answer of your questions. Otherwise, as Dennis mentioned before, that you also can contact us anytime via our email. So Dennis, now I would like to hand over to you. Thank you.
Thank you, Thomas, for a brilliant presentation. Now it's indeed time to proceed with our Q&A session. We received many questions through, so I would like to remind you that we will cover as many as possible during this session, and all the rest will be answered by Thomas after the webinar via email. So let's start with the first one. What kind of measurement method is typically used by Autotech to measure surface roughness?
Yes. The surface roughness, typically we have different method in here. In principle, there is a reason why, because customers sometimes they're using different method to evaluate. So, and also the other thing is, like, for example, the most commonly used is the optical confocal microscope. So with the laser confocal microscope, this is very commonly used by our customer as well. So in order to have a better comparison, what we measure here and what the customer measured there, so we are using the same method. So laser confocal microscope, and the other one is, as you can see, like for example, Nova 1WJ pre-treatment, that one. This kind of nanostructure usually is very difficult to define by laser confocal microscope. So we need AFM, which can go even deeper inside into the nanoscale. So that's why sometimes we also need to use AFM, so atomic force microscope. So those two methods are used very commonly in Autotech for surface roughness measurement.
Thank you. Our next question is for NovaBond EX. Why do we need to dry after pre-coating and before coating?
For NovaBond EX, no. I think it was a mistake. It should be dry after the pre-coating, before the coating, isn't it?
Yeah.
Okay, all right, yes. It is simply that, organosilane coating. This is the coating I already mentioned about is organosilane, so it's not a secret anymore. So the organosilane is very sensitive, not very sensitive. I mean that we need, it is aqueous anyway, this solution, but we need to maintain, the good balance of the water and also the other component what is inside. So that's why we try to minimize. We don't need like a drying. It's really a drying. It's only like a blow. Air blow is enough to remove all of the residues, because usually when the panel go horizontally, you will drag in a lot of water. So you just try to remove those water before it goes to the coating. Otherwise, it will influence the balance of the water concentrations with the other component inside.
Oh, okay, understand. Thank you. So the next one is how important surface roughness is to the signal loss performance in comparison to other factors like line design or dielectric types.
Yeah, actually, yes. Actually, the most, I think, the line design, right, and also the base materials, dielectric materials is really also important factor, very important factor. That's the reason why a lot of material suppliers outside there, they're very strongly developing, try to make a research and development about the new material with low decay, low DF. But the surface roughness also have a significant effect. So that's the reason why our OEM is talking to us, and please try to develop something which is low roughening or even non-etching at all, right? No roughness at all. I mean, they don't to keep the roughness as smooth as possible. So if I can say the number, if I don't remember wrong, from one of the report, is around the surface roughness has a contribution of around 7 until 8% on the overall signal loss performance.
Thank you. The next question is, can NovaBond be used on reverse treated copper foils and keep RZ value the same or minimize it to prior to photo printing / solder mask application?
Oh, very long questions. Okay, in principle, yes. Yeah, in principle, yes, we can use, but the reverse copper foil, usually they are really like, I think rough. I'm not sure. I'm not really familiar with this kind of material of copper foil materials. But I could say yes. But maybe I don't know who asked these questions. Maybe we need more details about what is the surface morphology or some surface properties is, and we can give you the best recommendation how to use it, and also for NovaBond EX, and which one, NovaBond EX or NovaBond EX plus WJ is the suitable process for you. So I would recommend that maybe you can write an email to me, and we will start from there.
How do you measure the thickness of silane on surface?
Okay, as to measure the silane, usually the most commonly used for us is two types. So one is the direct, not the direct way. I'm sorry. I mean that's more like that you can see it. I mean that like an FIB cut, so focus iron beam, and in combination with FESEM, yeah, secondary electronic scanning electron microscope, that you can make a cut on the cross section and you just see the silane layer directly. So usually we measure just from the cross sections. And the other method that we can see in here that we are using that also I presented is FTIR. So from the FTIR you could detect different kind of signal strength depending on the amount of the silane coating on the top, and then you can try to with some ways to quantify by integrate those signal. I mean that those spectra, and we can try to transfer into the signal of the thickness.
Okay, thank you. Is the coating of WJ different from the original EX coating?
Yeah. Okay. The coating is similar family, but they are different based on the organosilane still, but they are different in terms of not chemical properties, but it's more like a covalent bonding group.
Mm-hmm. Okay. What is the thickness range of silane coating in NovaBond EX and WJ process?
Okay. So the thickness is, I can just give you a range. Okay, anyways, a range is around 10 until 30 nanometer. This is typically when we try to have, the thickness is always, we can deposit as much as possible or as less as possible, but in order to have the best, the optimum performance, we need to control the silane thickness around 10 until 30 nanometer. This is the number that we got so far, which is can give you the best performance in terms of pill strength, the wedge void performance, and also SI performance.
Okay, thank you. The next question is why NovaBond EX plus WJ does not need to dry between pre-coating and coating SD, while NovaBond EX needed.
Yes. All right. So this is again because when we develop, actually it start first with the NovaBond EX and then come up with the NovaBond EX plus WJ, right? So it means that when we develop some things, we try to improve. So as I mentioned before, that there's also questions about the silane. Is it the same or not? It's not. It's not the same. This is still organosilane, but not the same group. So that's why in the WJ, actually, we already improved our silane. So this silane is less sensitive than NovaBond EX. I mean, in terms of the compositions of the aqueous solution, I mean, the water and the rest of the component. So in the formulation, we improve this in order not that sensitive with the water. So I mean that's the reason why then we don't need any pre-drying before, can go directly to the coating of for the WJ. And in order also to save money for our customer, then they don't have to build like, I don't know, like 1 meter more line, then they can save in term of this, then they can save more money in term of investment.
Okay, thank you. Reasonable. The next question is why no dryer is required before coating SD?
I guess it's the same question like before, right? No dryer required.
No. The question is why it is not required.
Okay, so I think as I try to okay, all right. So let me put it in this way: like the development of WJ is coming afterwards. So I mean that we optimize. I mean that we try to improve the silane inside of this as a coating. So in this formulation, the bath, or I mean that the silane solution itself is much less sensitive than the previous one. previous process, which is normally X, in terms of compositions ratio of the water and the other components. So that's why it's not necessarily for the WJ coating SD to have the pre-drying upfront.
Okay. So the next question is, which peel strength method was used for adhesion evaluation?
Right. The peel strength method that we usually perform is the 90-degree peel strength test. So where usually you try to create like a exemplar, I call it. So where you cut around 10 millimeter or 1 centimeter wide of copper foils. I mean that after you laminate, and then you try to cut to have 1 centimeter exemplar, and then you pull it, and the directions are perpendicular directions, where in the angle of 90-degree. So then slowly you pull out, and you got the number of the peel strength in every stripes.
Okay. Thank you. And the last question of today's session is, can WJ be used prior solder mask?
Prior to Sodomax, I can say
Yeah.
yes, yes, yes. And also, again, I think Sodomax, I mean that this process actually, I didn't show in here, because I would like to focus only on inner layer bonding. So that's why it's only for the IDF. For the Sodomax, yes, so it also can be used. We also have been tried on different kind of Tayo Sodomax, and then the performance is also good.
Okay. Thank you. So it's time to wrap up our webinar session. Thank you, everyone. We really appreciate you being here with us today. Soon you will receive the replay link for this webinar. If you like this session, feel free to share the link of the recording, which will be available to you after the receiver registers. For our upcoming and on-demand webinars, please visit autotech.com/media/webinars. We also keep you updated about our webinar schedule via email. Stay healthy and safe. See you next time. Thank you.